Hello guys, my name is PAULAM Paul. I'll be introducing you to the concepts of axial and centrifugal compressor for the course of aerospace engineering. Specifically, it is designed for cracking your gate exam, for going to your masters. So in this course, what we'll be dealing with are axial and centrifugal compressors. Before we get into the details of that, we will first know about the angular momentum, the work and compression of the axial and centrifugal compressors, performance of a single axial compressor stage, its efficiency, what we mean by degree of reaction, the axial turbine efficiency stage. So now, before we go into the details of axial and centrifugal compressor, we need to know what in which class these compressors actually come into. These axial and centrifugal is a domain of steady flow compressors. Now, what do we mean by a steady flow compressor? The compressor in which compression occurs by transfer of kinetic energy from a rotor are called steady flow compressors. If you have any problem regarding this video, you can comment on the comment below, or you can just pause the video and take it on a slower note. So now, as I have stated that there is two types of steady flow compressors, that is axial and centrifugal. Now here comes the question: which compression device will I be choosing when I am going to design something, say for an industrial use or something? That depends basically on the pressure ratio that we are that will be the predetermined pressure ratios that we need to know, that from how much pressure we need to compress the incoming air to how much more pressure. Depending on that, we choose either it's an axial or a centrifugal compressor. Now, normally for lower pressure ratios, that is, say you can 4:1 pressure ratio, we normally go for centrifugal compressor, as it is lighter and able to operate efficiently over a wide range of mass flow rates. Whereas for larger units with higher pressure ratio, we go for axial compressors because it is more efficient and is usually preferred. But make no mistake, there you can find certain units of centrifugal compressors also in high pressure ratios, that is like maximum of 1 or 2, not more than that. Now we will come for the centrifugal compressor in some time. Now let us go and see what is an axial flow compressor. Well, compressor we know is something we compress from one pressure to another, and what is meant by axial is that the inlet of air, the air which is entering the system or the machinery, is parallel to the axis, that is, you can see here. Now, you may have some questions about this diagram, so let us talk about this diagram at first. See, this is the rotating drum, or you can say the hub with the shaft connected. We are seeing a side view of the side cutaway of the axial compressor here. This is the drive shaft, which is actually rotating the drum. These are the delivery vanes, this and this. And in the rotating shaft, the rotor blades are mounted. That is denoted here by R and R, as you can see. Whereas in this casing is known as the stator casing. For simplicity, we will call it as the stator casing, because this is the casing which is actually used to operate a fully functional axial flow compressor. Now this S is known as stator blades, or static vanes, you can call them. Now axial flow compressors mainly consist of adjacent rows of moving blades and stator blades, that is fixed. As you can see here, it is an adjacent row of stator and rotor, and it goes on depending upon how many stages you want to design your axial compressor for. Now, the blades that are designed here, that is the rotor and the stator, as you have gone through the aerofoil theory in your aerospace engineering course, it is designed similarly here, but that is not the focus of this subject. We'll just pertain ourselves to work done and compression and all the necessary things that is needed with the axial flow compressor. So for your detailing, I have just labeled all the parts of the axial flow compressors here already, and I hope there is no you don't have any ambiguity regarding this. Now let us move to how it actually functions. As the air is coming in from this direction, the rotating drum makes the rotor blades rotate with it at the same angular velocity, and the stator blades, which are fixed, it is used for two purposes only. The first purpose would be it converts a part of the kinetic energy of the fluid into pressure energy. Okay. And the second part is guiding the incoming air into the rotor blades to the next stage, that is the next stage of the rotor blades, without any shock. By shock, I mean that as the air is coming in, it needs to be hit on the rotor blades at a certain angle so that it produces the maximum work done, or the maximum work is done on the air. So that thing is taken care of by the stator blades at each stages, as you can see. You can draw stator blades in this stage also, and a rotor blade in this stage also. Just for clarity, I'm just drawing one and I won't congest the diagram here. So this is the thing you get with the stator and the rotor blades. Now, as we are going through this, now let us go into the more depth of how we are going to tackle the subject. We are seeing this diagram as in the top view, sorry, as in the side view, as you're seeing with my pen on the view. Now, if we use a top view, that is you're using from, you're seeing this axial compressor from this direction upwards, you get a diagram of this kind. That is the rotor blades and this is the stator blades. For one stage I am showing here, you can add any number of stages you want, and we'll see that how we can efficiently use how many number of stages. These are the rotor blades and these are the stator blades. The air is entering the rotor blades like this. It can have subsequent stator blades here also, as I have stated earlier. The rotor blades are moving with a velocity that is C suffix BL. BL denotes blade and C is the velocity. As I have taken the freedom to already say here that C without any suffix is the absolute velocity with which the air is entering the system, that is air in. CR is the relative velocity. This relative velocity arises from the fact that as the air is moving in and the drum is rotating, there is a relation between the velocity of the incoming air with respect to the rotor blades, which we denote by CR, that is the relative velocity. Now, we have come this far with the notations and everything. So let us get to know how we are going to deal with the exchange of momentum and exchange of energy and work done. For that, we require a certain triangle known as the velocity triangle for for axial as well as centrifugal compressors. You can use it in centrifugal pumps as well, or as axial flow pumps anywhere, but it is of utmost importance and it is very crucial for you guys to know how to tackle the velocity diagram. For simplicity, I will be dealing with the mass flow rate of air, that is the air entering the system, to be 1. That is mass equals to 1 kg per second. And we'll denote with the dot up the m to say that to denote that it is mass flow rate. For simplicity, I have taken 1 kg per second. So you can for higher mass flow rate, we can just multiply it with whatever comes from the result. So that's not only that you don't need to worry about right now. Now, as I have in this diagram, as you can see, these are the rotor blades, and this is the incoming air that is with velocity c. So if I draw a triangle, with the incoming air velocity as c, I have this line. I have the absolute velocity of air, that is c1. Now, the rotor blades, I have said that it is moving in this direction. If you see this diagram from this point of view, that is from the up, you see the rotor blades moving in this direction. So the rotor blades moving in this direction will be given by CBL, that I have denoted here. Now, I have two portions of the triangle, and as you guys have learned in class in your 11th standard, that the vector triangle and the parallelogram parts. So if I join the two, the tail of it and the head of it, I get this relative velocity, that is CR. Now I have denoted for inlet and outlet conditions, I'll be denoting it as 1 1 1 1, and for outlet we'll denote it as 2. Now you may have the additional questions like, what are these angles? The alpha one we call the inclination angle. All right, we can denote it like this. Inclination angle, that is how much inclined the incoming air is with respect to the with respect to the blade and with respect to the axis of the compressor, that is alpha 1. The beta 1 is the inclination of the relative velocity with respect to the axial direction, that is this. Now, as you have seen that there is a certain angle with respect to the axial direction of flow for the absolute velocity, we can have two components for it, that is CF and CW1. The CW1 is the whirl component of the absolute velocity, whirl, WHIRL, that is whirl component of the absolute velocity, and we get a parallel component along the axis that is known as the flow velocity, that will denote with CF. This is the flow component and this will be the whirl component. Now we have gotten this with the inlet condition. We'll draw a similar triangle while the air that is entering this compressor in the axial direction is leaving this, like the air delivery. From the delivery vanes, we'll have another velocity triangle for the same, which we'll call the outlet velocity triangle. So I have taken the freedom to draw the same thing earlier also. This is the C2 velocity, that is the exit velocity that is coming out of the velocity triangle with an inclination of alpha 2. This is beta 2 for the same inclination with the axial for the relative velocity, and this is for the absolute velocity. Similarly, it will have two components, as you can see, CW2, that is the whirl component, and CF is the flow component. Now you may have certain questions about what is CRW1 and CRW2. This is the whirl component that is being given, or this is the whirl component that has been given by the relative velocity that is arising due to the difference between the velocity of the incoming air, that is this or this, and the blade velocity that it is rotating it with. So these are the two velocity triangles that you get. These are the two velocity triangles that you'll get once you start drawing it up, and just check for any irregularities or anything. Now from these two triangles, we will have simple basic geometrical constructions for the formulas. As you can see here, I have written here tan alpha 1 plus tan beta 1 is equals to CBL by CF, that is the blade velocity by the flow velocity. We refer to the inlet velocity triangle of here. We take the tan of alpha 1, we get perpendicular by perpendicular by base, and same for the tan beta 1, we receive this and we get this. Similarly for the, and we denote it with equation 1 for now because we'll be using it later. And for similarly for the outlet velocity triangle, we have tan beta 2 plus tan alpha 2 is equals to CBL by CF, as you can see here. And we will note it with equation 2. I hope up till now what I have discussed is clear with you all. If you have any problem, as I have stated earlier, you can let me know in the comment section and I'll attend to all your doubts that you have. Now, just keep in mind about these two velocity triangles, and if needed, you can review, go back on the video and just have this look over it, because we'll be moving forward to the other part now. Now, before we proceed any further, let us have a simple example or explanation for work done, the angular momentum, and such stuffs. So the first thing that we'll go with is work done. Work done we know is force into displacement. I'll run through this section a little fast because most of you have already know the basics of all these. So anyways, work done is equals to force into displacement, and I'm just using the cross sign here as a simple multiplication and not a cross product. So just take that into account. If I'll be taking any cross product, I'll let you guys know. Now, work done is equals to force into displacement, and if we take energy, we'll use work done per unit time, that is force into force multiplied by displacement upon time. That gives us force the video is shaky. So we get force multiplied by velocity. This is one concept that we'll keep in mind for now, and we'll see how we are applying it to the axial compressors and subsequently centrifugal compressors as well. This is, and now we'll move on to angular momentum. You can denote it with H or denote it with L. It is up to you. It's free of choice. Personally, I'll go with L. So angular momentum is what? Is a cross product of linear momentum and the radius. Here, the multiplication sign I'm using is a cross product and not a normal multiplication sign. We know the linear momentum is mass times velocity cross r. We have taken the liberty to denote the mass as 1 kg per second flow rate, or you can say 1 kg of mass. So we will use this, and for removing the cross product, we use the sine theta, the sine of the theta angle. Theta can be anything. That is the angle between the velocity vector and the radius vector. So L is equals to, we get this formula. Now, these are for especially the work done that I have showed you earlier. This is specifically for linear dynamics, but for rotational dynamics, we need to upgrade that. We'll be upgrading it with torque and angular velocity. That is, work done is equals to torque into, energy is equals to torque into multiplied by angular velocity. So as we have established these things, I'll let you know when and where I'm using which formulas. Now, as we have stated earlier in this part, that through the velocity triangle, though I have drawn the velocity triangles and everything, we still need to know how much work we need to put into the axial flow compressor, so the compression of air takes place as the compressor will be doing the work on the air. So for that, we'll require tangential force, that per kg of the mass, that is per kg of air that we'll be requiring. We require the work done, and work done, in terms of per stage, as I have stated earlier here, that in this diagram, this one this thing constitutes one stage. For subsequent stages, you can have as many number of blades, stator and rotor blades placed adjacent to each other. It really doesn't matter. That is one thing we'll go with. Okay, now, so the tangential force, that we'll be getting would be CW2 minus CW1. That is the wall velocity component of the outlet minus the wall velocity component of the inlet for per kg of mass. This is the tangential force that we'll be getting. I hope that this is clear with you guys. Now, the second stage would be to calculate the work done. That is per stage, per unit mass, how much work we are being doing. As I have stated earlier, work done would be what? This would be the tangential force that we have calculated. That is this force multiplied by the velocity, that is this velocity here, the velocity here. Let me just clarify this with you guys. Tangential force multiplied by velocity. This is not a cross product, this is a simple velocity multiplication sign. If it is cross, I'll write a cross over here. So my force, tangential force multiplied by velocity. So the velocity that that the air would be experiencing is the velocity from the rotor blades, that is CBL, which we are multiplying with the tangential force, that is the outlet wall component minus the inlet wall component. As you have seen earlier also, that during this work done and everything, I think all of you have gone through your engineering thermodynamics, and you know this formula very well, that CP, work done is also equals to the coefficient, the pressure at constant, coefficient of heat at constant pressure multiplied by the temperature difference, that is 02 and 001 is the inlet and the outlet conditions, that is the specific heat at constant pressure multiplied by the temperature difference, and this we are denoting with ACT, that is actual. By actual, I mean there is no theoretical temperature difference between the outlet and the inlet. We are taking the actual temperature difference that will be coming across. Now, work done per unit stage would then be, this is CBL we are taking, and we from the earlier earlier relations from 1 and 2 that we have seen, that tan alpha 1 would be CW1 by CF, tan alpha 2 would be CW2 by CF, and we'll be putting the values of these two here, and we get tan alpha 2 minus tan alpha 1 multiplied by CF, that is the flow velocity component, multiplied by the blade velocity component. We'll denote it the equation 4. The same thing we'll be carrying out for the outlet velocity conditions, and we'll be putting the same formula the same way it has been derived from equations 3 and 4. We'll use the same formulas for the derivation of equation 5, that is CBL CF tan beta 1 minus tan beta 2. Once we get this, we are actually in a place that we can just move forward with further formulas that we'll be establishing with the Euler's equation for 1 kg of mass or air, 1 kg of air being delivered. That is, the work done per stage now will be written as CBL2 CW2 minus CBL1 CW1. But If we follow the diagrams that I've drawn in the earlier page, we can see that CW2 minus CW1 is basically, we can rewrite it like CBL minus CRW2 minus CBL minus CRW1. This is the basic formula that we get from the diagram. So if I just reduce it up, we can see the CBL and CBL will get cancel each other, and we'll be remaining with two terms, that is the relative velocity, wall component of the relative velocity at inlet and at the outlet. So let us write that down. Which would be CW2 minus CW1 is equals to CRW1 minus CRW2. We get this formula, and further we know that CBL1 should be equals to CBL2 because since this holds, because as the blade is rotating, as I've stated earlier, for the rotor blades, these are the rotor blades that you see. So as they're rotating, the inlet and the outlet velocities for these rotor blades would be the same, because they're moving at the same speed. That is a part of a rigid machinery, and it does not have any independent movement about its hinge point, so that will have the same velocities. So now we can write the above equation as WST is equals to CBL multiplied by CRW1 minus CRW2, or we can also write it as CBL delta CRW. Delta CRW basically means these things, and we can substitute it with specific heat capacity at constant pressure multiplied by the actual temperature difference that we get. This is the work done per stage of the axial flow turbines. Now, if we use velocity triangles and cosine theorem, which I'm sure you have studied in your mathematics, we get this formula for the work done, that is per stage would be CR1 square minus CR2 square by 2 plus C2 square minus C3 square by 2. Now, this equation, we'll term it as equation, how many equations we are counting? 5, we'll have it 6. Now, the first thing that I'm going to introduce you is with the C3. What is C3? As I have already stated, that we are going to take one stage at a time. So for the first stage, as it is moving, like this is the stator blade, this is the rotor blade, this is again the stator blade, this is again the rotor blade. So for the first stage, we get that 1, it is coming in 1, 2, and it is again going for the other stage, that is 3. So that absolute velocity would be the third velocity, that is the outlet, that is moving into the second stage. That is the C3 velocity we'll be discussing about here. For the C3 velocity, how a diagram would actually look like is, extremely sorry for that. For a C3, how the actual diagram would look like is something like this. this would be alpha 3, and this would be the simplified velocity triangle that we get for the C3 purpose. But for this condition that we for the simplicity and for have getting an uh, uniform pressure pressure compression ratio and everything, we design each stage similar to the preceding one. So as a result, the velocity with which the air is exiting the first stage is normally or most of the time is equal to C1 unless it is stated otherwise. So we can modify this W work done per stage formula to CR1 square minus CR2 square by 2 plus C2 square minus C1 square by 2. So we are standing here with this. There is another term that I didn't state here, but we will be using it for centrifugal compressors and everything. That is CBL2 minus CBL1 whole square by 2. This term is actually missing in the axial flow compressors, but you get this term in the centrifugal compressors. This is because of this term only, the pressure ratio per stage in axial flow compressor is much less than that of a centrifugal compressor. The stage temperature rise regardless of the efficiency of compression will be given by this equation, that is del T actual. The temperature rise in each stage would be given by this CBL CF by CP tan beta 1 minus tan beta 2. We'll denote this equation as equation 7. I hope my handwriting is clear for you all to know, to read. This will be the equation. Many of you may have questioned how am I getting this equation for the each temperature rise. Well, let us go back to this part where I have denoted this in equation 3, that is work done per unit stage, per stage per unit mass. We get it done by this. And we substitute CW2 minus CW1, the values of it here. When we substitute the values of this and we equate this with the uh, this equation, that is CBL multiplied by CW2 minus CW1, the difference in the wall velocities at in outlet and inlet, we get the temperature difference, that is the del T, the temperature actual difference that we get from here. This is the stage temperature rise. Stage temperature rise means per stage how much temperature is rising regardless of the efficiency of the compression. That is how much efficiency we are obtaining by using an axial flow compressor with the various design stages or anything. Regardless of all that, this will be the temperature rise. Now, this we are almost done with the basic parts of it. Now we'll come to a cascade flow, that is the isentropic flow through a cascade, and how the pressure is rising through an isentropic flow when it is going through a cascade. Now, basically, a cascade means that, as you have seen here in the first diagram, just give me a moment. Yes. As you have seen in the very first diagram that I have drawn here for the axial flow, this one stage that we are considering, this is the first stage that we are considering here, second stage, and subsequently third, fourth, fifth stage, how many number of stages, that depends. So this kind of thing would, you know, build up a cascade flow, that is moving in cascades. So for pressure rise in isentropic flow, isentropic means that is the constant entropy flow, how much pressure will be rising when we are actually considering more than one stages in the axial flow compressor. For that, we will write down the Bernoulli's equation that you all know. That is P1 by rho plus C1 square by 2 should be equals to P2 by rho plus C2 square by 2. We are neglecting the potential head because we are assuming that both of inlet and outlet are at the same level. So we get the pressure head and we get the velocity head along with in the inlet, at the inlet and at the outlet. Now, the isentropic pressure rise may be expressed in terms of the inlet dynamic head, that is this dynamic head. Like in this, we can write del P isentropic should be equals to P2 isentropic minus rho times C1 square minus C2 square by 2. This is a simple manipulation of the Bernoulli's equation that I have written here. Let the Bernoulli's equation be like this. Yeah. So this will be a simple manipulation of the Bernoulli's equation that I have taken. That is the isentropic for the inlet. Isentropic in terms of the inlet dynamic conditions would be represented like this. We move the P1 by rho and we move it here. So, this goes in this C1 minus C2 comes in one side, this goes in other side, and the multiplied by rho, and we subtract it from the P2 isentropic pressure and we get the isentropic pressure for the inlet in terms of the dynamic conditions, inlet dynamic head, you can say. Now we can further substitute it with the following formula, that is P2 of isentropic minus rho by 2 that we already have here. And using the velocity triangles, you can always skip back into the video, the earlier stages, and since you'll be drawing the velocity triangles along with me, so you can just see from the velocity triangles that I'll be using the Pythagoras theorem and substituting the values of C1 square and C2 square. That is CF1 square plus CW1 square minus CF2 square plus CW2 square. This is the equation that I will be writing. We assume a constant flow velocity, that is the perpendicular or the parallel to the axial direction. So flow velocity will be constant, and hence CF1 and CF2 will get cancelled. So further, the isentropic pressure rise at the inlet would be rho by 2 CW1 square minus CW2 square will be this. Or we can also write it as rho by 2 CF square, putting the values of CW1 and CW2 from the previous equations that we have encountered, that is tan square alpha 1 minus tan square alpha 2. We'll have this equation as equation 8. Now, we have all the ingredients needed, that is the basic pressure, isentropic pressure rise, and what you need to know about the work done we have gone through. Now we'll come to the most important part, that is the degree of reaction for an axial flow turbine. This is the one of the most important parts for the topic, that is DOR, or degree of reaction, which is basically we'll denote it with by RT. This is the pressure rise. This is the ratio of the pressure rise in rotor blades by pressure rise in the whole stage. In the whole stage, I mean just one stage. Like, as the air is moving from the stator blades to the rotor blades, it completes one stage. So how much pressure we are, it's being, uh, how much pressure the air has, air pressure has increased from the stator to the rotor blades and coming out of the first stage. That is the pressure rise in the stage. This will be pressure rise, and this will be pressure rise in the stage. And this is the pressure rise in the rotor blades. That is on account of the rotation of the rotating drum, as I have seen, made you guys see from my earlier diagram, or the first diagram. That is the degree of reaction. Now, degree of reaction has other meanings also, but we'll come to that later. Let us just focus on how much how we should calculate the degree of reaction, and for the physical implementation, I'll come to that later. So the RD should be for pressure rise in the rotor blades, as we have already seen, that is work input per stage is given by, sorry, work input per stage is given by CBL multiplied by CW2 minus CW1. And the pressure rise in the rotor blades is at the expense of the kinetic energy. That is the, you know how much pressure is rising in the rotor blades will be obviously with the, at the expense of the kinetic energy. So pressure rise in rotor blades would be Ke is kinetic energy, which will be equals to Cr1 square minus Cr2 square upon 2. So when we put this base, we got the two values for pressure rise in rotor blades and pressure rise in the, stage, in one stage. So if we put the values in, we get this formula for the degree of reaction. This is the formula for the degree of reaction.